Hi everyone, this is Cynthia Hartley and I will be walking you through the Chapter 11 tutorial on raster analysis in the Mastering ArcGIS Pro textbook. As with all of my other walkthroughs so far, I am using the software version for ArcGIS Pro 2.6.1. There are a couple differences between the software and the version the textbook uses, so I will point them out as we get there. This is definitely the best chapter in the book, and really what you've learned so far has led up to this point. If you go on MGIS, you will more than likely be using many of the tools we are using in this tutorial. As ever, be sure you understand what you are doing and not just following the steps. If you understand this tutorial, the exercise homework, I guarantee, will be a lot easier. If you get stumped on that part of the homework, and this is the applied part of the homework, come back to the tutorial, look for the section that has a similar kind of problem, and that will guide you through that part of the homework. So the first section we are going to be working with Boolean overlays, and this is going to be steps 1 through 13 we'll do in this section. We are actually going to be doing a couple different suitability analysis examples in the tutorial today. This is going to include the snail habitat analysis from chapter 10, which we did using vectors. So as you're doing the tutorial, just really keep in mind that understanding Boolean overlays is critical to being able to do your exercise homework this week. So navigate, like we've done so many times, to your C drive or wherever you have your class data stored. Go into class projects, and this week we're working in the Raster Analysis folder. So open up your Raster Analysis project file. All right, so once your project opens, it will look just like this. And the first thing we're going to do is we're going to set some things in the environments. Now, because we are going to be doing analysis with rasters, and each raster is based on a grid. It's entirely possible, in fact, it's more than likely, if you're working with different rasters, the actual grid is going to mismatch. And so we need to control that because you can't do analysis unless your grids line up perfectly. So go up to your top ribbon here, and in geoprocessing, open up environments. And take a note. This is actually really handy. You can set your workspace, and the default is that the workspace and your Scratch workspace both go to the same default geodatabase. And we're going to keep this the same, but I will often set my Scratch workspace as something different. Let me highlight this. So I encourage you to take a look at this and read what it's about. As you know, a lot of times when we're working in GIS, we spin off a lot of files that we end up not using, and it can really clutter up your default geodatabase. So I really like using a Scratch workspace. I actually feel a little freer just to explore and spin off all kinds of new files. And then the ones you keep, you can specify to send them to your current workspace, which is where you keep your files that you want to work with long-term. Scratch workspace, those are basically your throwaway files. So we're going to keep that the same for now. And what we want to do, we're going to set our processing extent. So this controls the amount of area when we run a tool, what it actually looks at. If you click on the default, you can pick all kinds of things, but what we're going to do is we're going to go for same as layer. We're going to use the elevation layer. And this new set of coordinates, it defines a box over our map where all the tools are going to operate. And the next step is a little different in my screen than what is in the book. I think this is a difference in the versioning of the softwares. So it will probably look different on yours as well. So it looks like in the book that a window should open up here in your processing extent to set the to snap the raster to whatever you specify. But instead it's actually down here, at least in my version of the software. It's right here, it's under Raster Analysis. So we're gonna snap our raster to the elevation. So what that's gonna do, it's gonna set the grids, all the grids that we're gonna be working with, to the same grid as the raster elevation. And then we're also gonna go and we're gonna change our cell size the same as layer elevation. So your cell size is important because even if you set it so that your tools are going to snap to this particular elevation grid, it doesn't mean that all your cell sizes on all of your rasters are going to be the same. In fact, more than likely, there's going to be some differences. So what this does is it tells the tools to be sure to use a grid that matches this particular raster. And that will ensure that not only does your tool snap to the elevation, but then any rasters it's going to generate as part of its processing, it's going to match the elevation. So it just ensures, it's another way to ensure that everything matches, and you have to set all of these things. So if you go on and after this class, you're working analyzing rasters, which is more than likely, I'm sure several of you will, as part of your capstone or other projects. It's important to understand this. You're going to want to come back, and I'm sure at that point you'll come back to your book and you're going to look this up and refresh your memory. So I also encourage you to go through here and mouse over on the information icons and read about these different settings. So it's really set in your mind what this is doing, so you can use it in the future. So let's go on. So we've made it through step 1. So let's start our first section, performing a Boolean overlay. So before we jump in, just a note, when we're searching for tools up here in the geoprocessing pane in the search field, we'll probably see a lot of the tools show up twice. It's the same identical tool, but there's different extensions. And the ones that are relevant to what we're doing this tutorial are Spatial Analyst and 3D Analyst, and they share the same tools. So that's why they're going to come up twice. For the purpose of this tutorial, we'll go with the tool that is in the Spatial Analyst. Okay, so what we're going to do in the first part of the tutorial is we're going to rework the snail habitat assessment that we did, or analysis that we did in chapter 10. So in that chapter, we were working with vectors. Now we're going to repeat this using rasters. And it's, in some ways, it's actually a lot more powerful. It's interesting that you get a chance to do this both ways. How we're going to start is we're going to be looking at elevation. And we learned last chapter that snails prefer elevation between 1,200 and 1,600 feet. And so what we're going to do is we're going to take our elevation raster and we're going to reclassify it so that all of the elevations that meet the snail habitat requirement, we're going to classify the value for each of those cells as a 1. And the ones that don't meet that criteria, we're going to reclassify them as a 0. And we're going to start by using our reclassify tool. So type that into your search bar. And here we have the two, they're identical tools. We'll just go, for the sake of the tutorial, with this one, Spatial Analyst. So set your input raster to elevation. Reclass field, just so we understand, this is our raster, so it's our grid system, and each of these is a cell. And if I click on this, any of these cells, it gives us the value. So each of these cells has an elevation value. So we're going to reclassify these values. We want to classify our perfect snail habitat elevations as a 1, which is, in other words, true, and everything else is going to be a 0. So that's what makes it Boolean. It's true or false, or if you make it numerical, 0 or 1. So we're going to click on this classify and tell it how many classes we're going to have. So there's going to be 3. Now what's happened here is it's automatically populated the minimum value and the maximum value, and then divided these categories that we told it to do 3. So we're going to change this. We're going to control this. So our snail habitat is between 1,200 and 1,600. So everything below 1,200 is going to be, the new value is going to be 0. And then this is going to be a 1. These values are going to represent the range that snails like. So that's going to be a 1 or true. And then everything else, we're going to make sure is a 0. So our new value, we have to change this to 0. And the no data, we've encountered this before. That's that when you display a raster and you have a big black box around, which represents null or no, there's like no values in the cells. So we're going to also make this a 0. Oops. So now this is going to generate a true Boolean raster where it's binary. So it's either a 0 or a 1. And we're going to change the output raster name. Here's that default geodatabase that we saw in the environments. Elevation range. And run the tool. So it looks a lot different. And if we click, mine came up brown and purple. So if I click one of these brown areas, this new value is 0, and purple is 1. And we're going to fix these colors. So right click where it says 0, I've got the brown, right click on that, and we're going to make that a 10% gray. So it's the second one down. Let's zoom out and get a better look at what this looks like. And in our book, it's green, so I'll go ahead and change it to the green so it's consistent. So you should have something that looks like this. So next we're going to work on the vegetation layer. So let's turn off everything else and turn on vegetation. Let's turn off the roads too. So this vegetation layer is familiar. This is what we used last week in chapter 10. So this is a polygon layer. So it's a vector, not a raster, but we're going to turn it into a raster so we can use it in our raster analysis tools. So we're going to open up the tool that will do that for us. So search on feature to raster. Feature to raster. This converts features or a vector to a raster data set. So we'll set our input to vegetation. And the field we're going to convert into our raster is going to be density 96. There it is. And the reason we have to select this field or any field is because rasters only store one value in their cells. And of course, we know vectors can store many. Let's open this up and take a look at the one that we selected. So here's the field that we're going to bring across into our raster. Change the name of the output. Veg density. Run the tool. Okay, so our tool has run. Let's take a look at the new raster we just generated. So turn off the vegetation layer. And it looks pretty crazy, and it kind of actually looks like the boundaries are the same as this old polygon layer. So if I highlight that, you can see it's got this kind of crazy polygon shape. But let's turn this off. I'll clear my selection. Turn off the vegetation layer. And if you click on any of these. You can see it doesn't retrain those old polygons. In fact, if you zoom in, you can see it's been converted in this real kind of chunky square cell values. Let's move this over. So this looks like one cell. Let's just measure this distance. See what it gives us. Yeah. So 30 meters. So back when we set the environments to give us 30-meter cells, that's exactly what we've got. Let's go back out. And if we open up our table, our attribute table that we just generated, based on the new cells that were created and how they overlap with the old polygon layer, we've got like almost 150,000 cells that correspond to the density 0 from the initial polygon layer and on for these other A, C, and B. These are the number of cells in our new raster that have those values. And the actual value residing in the cell corresponds to these integers. Raster can't have a text, a letter as a value. It has to have a number. So these are the actual values, but it's in the table of contents here, it's interpreting them based on the column that we selected when we brought the raster across. And if we click to identify, here's our density B, but the actual value is 4. And our book asks the question, how would we calculate the area of, say, any of the classes? So the book asks for class C. So we know that each of these cells is 30 meters. So you just do a multiplication. Okay, so we're going to reclassify this. Again, we turn this into a Boolean raster. We're going to use the tree density values that we know snails like in their habitat. So let's go back and open up our reclassify. So I went back all the way to the geoprocessing pane into favorites, and reclassify is here. Our input raster, of course, is veg density. And it automatically comes up with density 96 as our reclass field. And we could do any of these others, but we know that C is the thing that snails like. So we're just going to change everything else to zeros for the new value. C is going to be a 1. So again, Boolean, even the no data. We want everything that we don't want to select to be a 0. And our output raster, dense trees. And run. And our tool has run. We should have something that looks like this. Let's change our Z value to gray. And I'll stick with this kind of purpley color since that's what's in the book. And so because the field in density 96 is not a number, it's a text. It just combined all of these values. So we're gonna change this so it's something that we recognize as a Boolean raster. So we're just going to change the value field. And now it's really, that's really painful. Let's go back and fix that. We'll go with kind of a purpley. Let's stick with the book look. Okay, so that's what the textbook figure looks like. This is B in figure 11.22. So our last feature we need to fix is geology. And so let's, I'm going to turn off everything else. I want to focus on geology. Dense trees goes. And we're going to turn on geology. And let's take a look at this attribute table. So we know what we want here is limestone. So we were working with this last week. Here's a couple limestones. So there's quite a few different rock types. So we're going to take another approach to get to the same place. Let's do select by attribute. And I prefer to do it this way. You could go up here and open up one of these icons, but again, I don't like a window floating over my map. Layer by attribute. So input is going to be geology. And we want to tell it to give us rock type is equal to limestone. And I'm just going to select it from this list. All right, so now all our limestone is selected, and we're just going to use the feature the raster tool, which is also a new one for this week. So before we were doing feature to layer, now we get to use the feature to raster tool. And again, we have a selection. Input's going to be geology. It's only going to act on our selection, which actually I've seen on homeworks some strange things where some of the answers were getting smaller attributes and smaller numbers of attributes than what there should be. And I have a feeling some of you are running your tools with a selection on your layers. So we're going to pick our field. And again, remember, we are converting from polygon to a raster. Raster can only have one value. So we have to pick one of our fields. Of course, we're going to pick rock type. And the output raster is going to be limestone. So we've got just our limestone selected. So when this converts, it's only gonna take the selection. So let's run. Put limestone above. Interesting, it picked black. I've never seen that before. So there's our limestone. Turn off geology. In the book, it's kind of a red, kind of a brown. There we go. So let's take a quick look at our table. And we just brought across limestone, as we knew that was going to happen. However, that causes us a bit of a problem, because if I click outside of the limestone, we get no data. And if we click inside, so we have rock type limestone, and our value here is 1. Our value here is no data. So this actually isn't a Boolean. So really the way to deal with this, and because we want to compare this against the other Boolean rasters, or we want to run a tool with the other Boolean rasters, we really need to do a reclassification. So let's go back. I'm going to go to my favorites and open up this reclass tool. So we're going to reclass limestone. And here we have our Boolean limestone's a 1, no data. Let's make that a 0. And we're going to rename this raster. Limestone Boo. Run. So for consistency, I'm going to change this to brown. Let's just turn off this other one. And to double check our values, if I click inside where it's brown on the new limestone Boolean layer, value is 1. If I click outside where there's nothing, value is 0. And our rock type here is null. That's because it was no data to start with, which wasn't an actual value. It was just no data. And to double check our attribute table, here's our limestone and our 0. So here's our Boolean. Okay, so now we have our 3 layers that are all Boolean, and we are ready to do our suitability analysis. And what we're looking for is where in space all of these layers coexist. And anywhere where they don't coexist, we're not interested. So we're actually going to generate another Boolean layer from this that will give us our snail habitat. And there is an easy way to do this. All we do is we're going to multiply each cell. And if there's a 0 in the cell, meaning any of these conditions don't exist, the output's going to be a 0. If they're all 1s, meaning they all coexist, then the output will be a 1. Again, that will be our Boolean that will give us our snail habitat. So let's go back, and what we're going to use here is our raster calculator. So we're going to multiply the layers that we're interested in. So I'm going to double click on limestone Boolean and then hit the multiply. And then we want dense trees, multiply, double click on multiply. I'm just going to go back and put that in there. And elevation range. And the name of our output raster, snail hab. Okay, some pretty bright colors. let's change these colors. So let's turn our 0 back to 20% gray. I want to turn off, and see I don't have any layers on top of this on. I think I've got everything off. So let's just have our snail habitat layer on, and let's not have that be that pink color. We're going to right click on that. Let's make it kind of a dark green. Compare what you have. It should look like this. I think my layer looks a lot like what's in the book. I think this is accurate. So here's our snail habitat, and this is equivalent to figure 11.22D, and this is looks pretty right on. It's brown in the book, but you should have something that looks like this, whatever color you pick. And so this is our Boolean, but because we have rasters, this also gives us the ability to rank. So maybe a snail would be willing to take 2 conditions and not 1, maybe not be quite as happy with it, but it still might do in a pinch. So let's create a ranking for this. So we'll go back to geoprocessing. And what we're going to do is we're going to add these instead of multiply them. So I'm just going to highlight, oops, I'll just have that delete, and then I'm going to click on plus, double click on plus. Oops. You could just go back and retype the whole thing, but I think this works. So we're going to do snail hab rank and run. So our tool is run, and let's fix these colors so we can see what's going on here. So I'm just going to go into symbology, and we're going to go with a light to dark green color ramp on this. I can find one. Actually, here's an easy way to do that. Here's greens. So what I did there is under my color scheme, I clicked on show names, and that's sometimes a pretty much easier way to find your colors. So this looks really good. You should have something that looks like this. It gives you a ranking from 0 to 3, with 3 equivalent to our other snail habitat. This is equivalent to figure 11.25 in the book. And so that was step 13, and that brings us to the end of the Boolean raster section. Don't forget to save your project. And let's take a little break if you're ready and you want to go back and rework some of this, and then we'll start the next section. Okay, so we're ready for the next section, distance functions and buffers. And this corresponds directly to what we did in chapter 10, where we buffered the roads around snail habitat. So we're going to do the same, but now you get to see how this works with rasters. So this is our map where we left off. What we're going to do is we're going to turn off and collapse everything we had just created. Just closing everything down. I like to collapse all of these because it just really cleans up my display. So we're going to work with roads. So turn on your roads layer. Turn off everything else. We're going to start by going into our geoprocessing pane, and we're going to open up a tool called Euclidean Distance. So I've moused over this little help icon, and it brings up a graphic that kind of explains this tool. And in this explanation, we're setting a source raster that we're going to calculate distance to. So we've got two items on here. This is one grouping, and then down here in this lower corner, this is a second one. So what we're asking the tool to do is tell us the distance from each one of these cells in this raster to the nearest source. So it's going to give us all the distance from this grouping of cells that are right next to it. And this is the corresponding output here. And then the further away you move on these cells, the closer you get to this other source. And when you're actually closer to the other source, it will give you the distance from these cells to this other source, and same across the whole grid. So what this is doing is it's giving us a surface from each cell in the raster to the nearest source. So that's what we're going to do with our roads. So let's close this and go ahead and set up our tool parameters. So our feature source data is the roads, and we're going to change this. Distance. I'm setting this up like the figure on 11.26 on page 357. It looks quite a bit different on my screen than it does in this graphic, this figure. And that's because of the changes in the software. So they've added quite a bit here. For this exercise, we're just going to stick with what's in here. This topo 30 meters, this is the elevation layer. The feature class is topo 30 meters, and we're already set this up in our environments. So we're going to stick with that. It's referring to the grid in this raster. And we're going to ask for one more thing. We're going to ask for an output direction raster, which is here. We're going to call this road direction. So let's mouse over, see what information this gives us. So think back to the little graphic we just looked at up there in help, where it gave us our grid and our source features. And instead of giving a distance in each of the cells, it's going to give us a direction. So let's mouse back over that. I think it'll be clearer if we look at it this way. I just opened up the web page, I clicked on it, which is probably a good thing to do so you can take a look at this and get more acquainted with what this does. So here we've got distances. Now in our direction raster, instead of a distance, it's going to give us a compass direction. So if you were standing on this grid here, the cell here, what is the direction to the closest cell? So it would be this one. And so if you're out here, say, what is the direction to the closest cell? And it's going to be, these are our three source ones. So it's going to give you the compass direction to this. A little bit of a challenging concept, but once we generate this, it'll be clearer. So let's run the tool. So our distance raster gives us this kind of crazy psychedelic look. Let's turn this off for now. Let's open up the symbology for our road distance feature class. So my tool has, after this ran, it defaulted to a stretch symbology. And the book tells us to open up our symbology, and I think perhaps in the old software it would default to a classify. So we're just going to switch to classify for now so we can explore with the book. It looks like from the book we should expect that this would default to a different method. Let's switch to equal interval because that's what it mentions. It says that equal interval is normally appropriate, which is something that we've discussed, that the normal default, Jenks, isn't necessarily the best choice. But in this case, clearly this is not telling us anything. So what's going on here, we'll go back to natural breaks. See, that does look better. If you click on the histogram, you can see that there's, in the second break here, we've got more cells populating this. We go back to equal interval. See how skewed this is? All of our occurrences are in this one break here. And the reason for this is because there's an area up here that's quite a distance from any road at all, much more so than any of these other rasters. So it's skewing our data. So here's a case where you'd probably want to explore this. That's geometric. And you can see this histogram shifting where these other breaks, there's a lot more data, and that's why this is shifted more toward the red end of this particular color scheme. And how about equal interval is what we were looking at before. Yeah, there's that. So let's stick with what the book is saying. We're going to go with natural breaks. I'm still not convinced this is the best one because we still have an enormous amount of yellow and just a little bit of orange on here. So let's just zoom in here and get a better look. So if I click on one of these rasters, so what this pixel value is, it's going to be a distance in meters since the unit of this projection is meters. So if I click right next to the road, that's 30. So it's probably a pixel sitting right on the road. Actually, that's a pixel sitting right on the road. I get a little further away, 60. So it's going up by increments of 30 as I go evenly away. So let's go back to where we were before. So this is a continuous surface. So switching on our road direction, this crazy psychedelic look. Turn on, oops, let's make this so we can see what's going on here. I'm going to, okay, so here's the symbology. So each one of these classes gives us a compass direction. So if you're standing in any one of these cells, it'll tell you the direction to your closest road. So that's a compass direction of 255 as opposed to, let's see, yellow is 90 degrees. And if you click on this red, it's 0. Maybe not the most intuitive, but this is a good example of some of the functionality of this tool. Okay, so I'm going to shift gears. Let's turn off our road direction layer. So now let's suppose that we want to create a new feature class that's going to show us essentially a buffer up to 300 meters to the road. Or we want to know all of the rasters that are within 300 meters of the road. So let's open our raster calculator. See if I have this. I don't have it on my list here, so I'm going to type this in. Raster calculator. So we're going to type in the expression road distance. Oops. We want this one is less than or equal to 300. And we're going to name our output road buff 300. So you should get something that looks like this. This looks like figure 11.28 in the book. And let's make our colors look a little more like what we've got on our text. So let's, for the 0, let's do gray 20%. And it looks like we've got green. Not that bright. Okay, that looks like what I'm seeing in the textbook right now. Okay, so for the next part, this is, we're going to start with step 18. We're going to classify this habitat based essentially on safety for the snails. We know that snails rarely travel more than 400 meters. And we also know that they tend to wander into roads and get crushed. So we want to rank habitat based on distance using 200-meter, what we call ring buffers. So we're going to do this using the reclassify tool. So I don't think I have this up. No, so I'm going to have to search for it in my search pane. So we're going to set our input raster to road distance. We do want to reclass on the value field. So let's click down here on the classify link. We want to specify that there's going to be 4 classes. And we're going to have our first class be 0 to 200. I'm following figure 11.29 in the textbook. Second one, 200 to 400. $400, $600. And then this one essentially is all of the rest. So I'm going to name the output ring buff 200. So what we have generated here is a feature class that shows distances from the road represented by buffers at increments that we've specified in our reclassify tool. So these aren't actual snail habitat. It just represents distances in relation to snail survivability. So what we have to do next is find out where this overlaps with snail habitat. So now what we're going to do is we're going to multiply this times the snail habitat. Let me collapse these so we can look at it. So snail habitat here, 1 signifies snail habitat, 0. None of the features we're looking for exist for the snails. So if we multiply this raster times the ring buffer raster, it's going to give us a new raster, but the numbers are only going to represent, so essentially this raster here, but it's going to get rid of all of the habitat where snails can't live. So let's go back to our geoprocessing pane, and we want raster calculator. And we're going to create an expression, snail habitat times ring buffer 200, which is up here. And we're going to call this dist habitat. Dist habitat. So now the tools are taking a bit longer to run because we're doing rasters. There's a lot more data with the rasters. So let's turn this to our null color, which is, so just turn 200 to this 20% gray. We're going to then change 1 to red, 2 to orange, 3 to yellow, and 4 to green. And turn off our ring buffer. So this looks like figure 11.29 in the book. So this is the same analysis, or essentially the same output as the analysis we did in chapter 10, where we were finding snail habitat using vectors. We did an intercept where we had our 3 different criteria for what snails like in their habitat. Did an overlay, we found out where they all exist in space. This was different. This was a Boolean overlay that we did with rasters, where we coded the required habitat with a 0 or a 1, which is Boolean. And then we did a multiplication to come out with where in space they coexist. With both methods, then we did a buffer exclusion to find the parts of the habitat that was furthest enough for the road to be compatible with life for our snails. So 2 different ways of coming up with a similar analysis. Only in this case, we also added in this ring buffers where we're looking at various distances from roads. Okay, so let's pause here for a moment and think about what we've done. Let's make sure we understand the difference between the distance rasters and the buffers. So let's compare ring buffer 200. Expand that so we can see road buffer 300. And road distance, let's move that up 1. So make sure you can see, it's like my map needs a little more space here. So understand the difference between a distance raster and a buffer. I'm going to just turn off everything but our distance raster. And you can tell even just looking at the legend, and oh, by the way, if you were to symbolize this in a legend, you would make sure that we didn't have 6 decimals here. You would cut this way down or possibly to no decimals. But aside from that, this entire map is made up of these little cells, and each cell has a value. Here's our pixel value, 742. So each one is a cell with a different value. Whereas, if we look at our road buffer, each cell is either a 0 or a 1. So this is a Boolean raster. In other words, it's binary. Whereas this is a continuous raster. And buffers are much the same. Each one of these, actually what we can do is open up attribute table. And here's our values. Numbers, 1, 2, 3, 4, they're more like categories. So it's not relevant to an actual measurement or a piece of data. So even though we can symbolize our continuous raster to look like it's a buffer or a Boolean, it's not. Each one of these cells has a continuous value. So let's do a little demonstration to bring this home. So we're going to open our Euclidean distance tool here. For input, let's put roads. Output will be minimum distance. And distance. And we're going to enter a maximum distance. And let's mouse over this to see what this means. So what that's going to do is putting a limit on the values. And in our case, we're going to make it 300 to correspond to our road buffer 300. Map units are meters, so that will be automatic. We're not going to mess around with the direction raster this time. So run the tool. So let me turn off the lower layer. So just like the last time we ran this tool, it gave us this interesting classification, the stretch. Just zoom in. So you can see the pixels here, or the cells. So each of these cells has a value. I'm just going to kind of click my way out. So this is our road, which I just clicked on. That's the layer, but let's just go out a little bit. Yeah, so here's our 30. We're like one cell out from the road, and as we go out, the number gets bigger. So each of these cells has a value, and when you get out here, you have no data. So if all of these were the same color, it would look like a buffer. It would look like this. Turn that off. So it covers the same area. In fact, I bet the pixels are exactly the same. Yeah, so our pixels are identical, but that's because of the environment settings. We're forcing it to use the same cell size and to snap to the raster grid. So Boolean overlays are important when we're doing suitability analysis or habitat analysis. However, you wouldn't be able to do this with this distance buffer. What you'd have to do is go in and reclassify. So everything here, you'd have to reclassify to a 1, and then everything that was no data, you'd have to reclassify to a 0. So just remember that when we're talking about Boolean, we're talking about a binary data output with zeros and ones. And if you're doing a Boolean overlay, all of your layers that you're working with have to be Boolean. So you can either add them or you can multiply them to do your suitability analysis. So that is it for this section. We just finished up with step 21. Here's where we'll stop. If you haven't been following, go ahead and run through these steps or take another look at them, make sure you understand, and then we'll move on to the next section. So our next section is topographic functions, starting on step 22. We're actually going to be driving everything we're going to make on this next section from the elevation raster. And even though it's a grid and each cell in that grid only has an elevation, it allows us to do a lot of really cool things. So this is the map where we left off. We're going to say goodbye to snail habitat. In fact, let's neaten everything up and save your project if you haven't done so already. And we're going to start a new map. Insert new map. And while we're at it, we'll close the Sturgis window. So we're going to change the name of this map to Topo Functions. So start by turning off the topographic base map, since we're going to be making our own topography. We're going to add that Topo 30 raster from the Black Hills. So go into your folders. I've got Black Hills in here. Sturgis. And here's topo 30. So just drag that over into your map. So the whole premise of this part of the tutorial is that we are looking for a place to build a winter ski cabin. So we've got this big elevation area, and we're going to do essentially another suitability analysis where the two things we're going to be looking for are slope and aspect, because we want to build our cabin in a flat area, and we want to put it somewhere where it's going to catch a lot of the winter sun. So we're going to want a southerly exposure. We're going to start with the slope tool. So slope is a function of elevation. It's really how quickly the elevation changes from one point to the next. And since we have a raster that's all full of cells with different elevations, we can calculate the change in the elevation in between those cells. So we're going to open up the slope tool, go to geoprocessing, type in slope in your search bar. So our input raster is the only thing we have a choice of right now, the topo 30M, 30 meters. And we're going to rename this slope 30 meters. So we're going to stay with degrees for your output measurement. Percent rise is another choice, but degrees are good enough for now. Z factor default is 1. We're going to keep that. We can keep our method and run your tool. And here's our slope. So the first thing we're going to do is look for an area that is pretty flat. So the directions are telling us to look for areas with a less than a 10-degree slope. So we're going to do this by using our raster calculator. All right. So let's type in an expression. Slope 30M is less than, I always forget to double click, less than 10. And we're going to rename our output raster slope. Run the tool. So we're running rasters now, and there's a lot of data. This entire thing is a grid with data in it, so these take a little bit longer. So let's make these colors work for us. Change the null value to 20% gray. Yeah, so this works for me. And we can explore this a little bit. Of course, we know that these gray areas are going to have values of 0, and the pink areas are going to have a pixel value of 1. Let's look at the same area on our slope. So these wider areas correspond to our lower slope. So it should be about everything from here on down we're capturing in our purple areas. So that's a slope of 2 degrees, 9 degrees. Yeah. And then these darker areas, which correspond to the gray, are pretty steep, 22 degrees. So anywhere where we've got this purple is a potential cabin site. But now what we want to do is figure out which of these areas also have a southern exposure. So we're going to go back to our original, to our topo. Close this. Let's go back and get our aspect tool. So aspect, if we mouse over this, what this is telling us, it's the downhill slope of an elevation, which direction is it pointing on a compass? So essentially, this is going to give us a readout. It's like north-south, which is exactly what we're looking for. It's going to be our south-facing slopes. So let's put this into action. Topo 30M. We're going to rename this aspect 30M and run the tool. And here we go. So our labels here automatically populate with the compass direction and also conveniently the degrees of the compass. So what we're looking for is our southern exposure. So we're going to be looking for something around in here. So essentially kind of a green through a light blue. So what we're going to do is we're going to go back to our raster calculator again. And we're going to create an expression that's going to select just these directions. We're going to build this in a way that we make sure that we capture just the narrow range that we're looking for. So we're going to start by using parentheses. And we're taking from this raster now, our aspect 30M. Oops. Double click. So first we're going to enter everything that's greater than 130 degrees. And we're doing it this way so that we force the tool to consider this first. So when it runs, it's going to give us everything greater than 130. So like from here in the middle of our southeast, it will give us everything from here all the way up. And we're building an and expression into here. So these look a little different than what we've seen before on the SQL wizard. Instead of the word and, we're using the symbol. This here is an or, if you were going to use that. So all the same Boolean operators. So aspect 30M again. And then everything less than 230. So that's going to come over here and it's going to look at everything that's in the middle of the southwest classification and everything up this way. So these parentheses are going to force the calculator to look at these two separate selections and then do the and together. So you might recall when we do and, that means that both conditions have to be true. So this is going to give us an overlap that's just going to hit this area. If we were to do an or instead, that would give us the whole thing. With or, either condition can be true. If you were to use this on, say, another kind of problem, you have to think through this very carefully regarding what operator you're going to use and what that's going to give you. So we're going to rename our output southerly and run. And here's our results. So let's turn our null value to 20% gray. And to make this look a little more like the book, I'm going to change this to like a really dark navy. So these are, these kind of dark blue are where the sun is hitting our slopes coming in. You can imagine here, the south would be coming in kind of this direction across the landscape. So let's close down, collapse our aspect. We're done with the slope. So what we're interested now are these two low slope and southerly. So between these two, where our conditions are both true, that is going to be our cabin site. So this, again, is our suitability analysis. We want to go back to our raster calculator. And just cleared this out. And now we're going to type in a new expression. Low slope times southerly. So anywhere where these conditions are not true, and this is going to be raster by raster, it does this multiplication. Anytime we have a 0 where both conditions aren't true, the output's going to be a 0. In order for us to get a 1, both conditions have to be true, which is what we're looking for in this particular suitability analysis. So let's rename our raster cabin sites. Change the colors. Oh, let's go with kind of this dark green. So this corresponds to figure 11.31 in your book. You should have something that looks like this. And this is going to be where we're going to put our cabin. So that's it for the suitability analysis for our cabin site. We're going to look at one more thing, which is pretty cool. We're going to do hill shape now. So we just finished with step 27. We are now on step 28. So let's turn off all our cabin suitability. We're going to work back again with Topo 30M. Go back to your geoprocessing and open search for hill shape, the hill shape tool. So let's build this and we can talk about it as we go. Your input raster is going to be Topo 30M, and we're going to change the output name for this. Hill shape 30M. So there's two things we set here, azimuth and altitude. So I'm clicking on our information icon. So this is the angle of light. So think about this like a season. So in the summer, the sun rises higher in the sky. In the winter, it's lower. So this is the angle. So this essentially gives you your winter sun or your summer sun. And then the default is 315. And then the altitude, the angle of light source above the horizon. So think of this as the time of day. So 90 degrees is directly overhead, so that's essentially noon. So the combination of these two things, we can simulate the sun pretty much at any time of the year, any time of the day. We're going to leave all of these others with their defaults, but they're pretty interesting to play around with. Let's go ahead and run. So here's our output, and I'm just going to move this up to 30 underneath that. So if I toggle that off and on, you can see that it looks pretty similar, but the hill shape's pretty cool. Zoom into that. This is a really great thing to use as a base map. You can make your layers transparent, and then you can see your hill shape behind it. It gives it a really nice texture. There's a lot of cool effects you can do with this, and I've seen some of you submit some maps using this technique. So brings us up through step 28. 29 works with viewshed. We're not going to do that step, although I do recommend if you're interested in it. Essentially, you're looking, you import some points. In the case of the book, they're doing an example of fire towers. And what the tool does is it gives you a selection of rasters that show what areas on this landscape are visible from the viewpoints, and also what areas are visible from both viewpoints at the same time. Okay, so pause and explore now. If you need to go back and rework anything, now is the time to do it, and then we'll start with the next section. Okay, so now we are really going to shift gears. We're going to combine the next two sections together and complete steps 30 through 41. We're going to look at neighborhood functions, which I'll explain as we go. And then we'll practice converting a raster to a feature using the output from the neighborhood section. Okay, so this is where we left off last. We're going to start on step 30. So let's clean up our map, save it. If you haven't done so already. I'm going to turn off my layers and collapse all the symbology. So we're going to start with neighborhood functions, and we're going to bring in a layer file. So open up, go to your catalog, open up folders, go into Black Hills. We want this land use layer file. Now remember, this is actually referring to a feature class. This is not a feature class itself. It's actually coming in with symbology. Normally when we bring in a feature class, there's no symbology. If we check this properties on this, we can see the source. So this is in the Sturgis geodatabase, and it's a data set called land cover. So what we're going to do is we want to analyze heterogeneity in land use. And looking at this, you can see that there's areas that are very similar. This is all green down here. This is a forested area. And then up here, where it's developed, this appears to be a road. There's a lot of heterogeneity. So one of these cells in this raster is close to other cells that are very different. Let's see what this looks like if we hit explore. So our pixel value here is 71. So that's coded for the land use type that it is. In this grassland herbaceous, but this pink, I believe, is developed. So this pixel value is 22, and it's coded as developed low intensity. And so you can click around here and kind of explore this and see. So the actual value is a number, but the number corresponds to this symbology. So what we want to look at is a way that we can quantitate this heterogeneity. And we're going to start by using a focal statistics tool. And we'll talk about that as we go through this. So go to your geoprocessing pane and go back to the search. And I've already got focal in here. Let's see, I'll just hit return. So open up this, your focal statistics tool. And let's just mouse over the help. And the way this works, here's our input raster, and this is our output raster. And we're going to look at each cell one by one, and we're going to analyze all of the different number values around it. And in this case, a raster that's close to other land use types, there's going to be lots of different numbers that we're going to find around it. Whereas a number down here where it's all very much the same, all its neighbor rasters are the same, there's not going to be any difference. So for your input raster, we're going to do land cover, and we're going to rename it LC, land cover, VAR, probably variability, FOC. Now, I don't know that I would use a name like this. I'd probably try to make it something that's a little more obvious, but we won't worry about that. So the neighborhoods, let's mouse over this and see what. So this gives us a description of what we're trying to do. If you click on this drop down, here's all these different choices. And say you were trying to do this and you're thinking maybe there might be a better choice, just mouse over your information here. And there's a definition for each one of these different options. So we're going with rectangular. So we're already automatically gives us a choice of height and width. 3 by 3 is the default. We're going to do 10 by 10 because we want to look at a bigger window. Our unit type is cell. I'm not actually sure what map would give us, but cell is going to be essentially pixel or cell by cell. And let's see if this gives us a better explanation of this rectangle. So, so what we're going to do is we're going to each time this runs, it's going to look at one of these cells, and it's going to do this 10 by 10 grid around it, and it's going to see how much variability. Actually, I'm ahead of myself. So here's all of our different statistic types. We're doing variety. So this is just telling us how many different numbers there are in that 10 by 10 grid. We could add them all up. We could do the average. We could pick the highest number. So there's lots of different options here, different ways that you can choose your output. Standard deviation might actually not be a bad option for variety, because that is a function of variation. But we're going to do variety. So let's run the tool. Now, there's a lot of math going on here, much more than anything we've done so far. So I'm going to pause the recording while this runs. Expect this to take a while. Okay, so my tool has run, and this has given us this kind of crazy looking pattern. What's happened here is it has symbolized it with essentially unique values where there's no relationship between these numbers. But in this case, there is. And what these numbers mean are that any cell that had all the same land cover types in its 10 by 10 grid around it, we got 1. So this is the number of different land use types. And all the way up here to 9, any cell where all 9 of its neighbors were different, we got this 9. So let's change the symbology here to something more appropriate. In this case, we're going to want a graduated color ramp with 1 color. So let's go to symbology. And I think what I want is toward the bottom, yeah. So the book tells us monochrome, but I kind of like this 2 color. So let's see what this gives us. That's okay. Green to me means trees. So maybe let's just go with something a little different. How about, yeah, I like that. So this isn't monocolor, this is a bicolor ramp, but I think it illustrates what we're looking at pretty well here. So anything that's a 1, a lighter color, it's a very homogeneous area. All the neighbors are the same, all the way up to a 9 here. And if we toggle this back and forth, here's our development area. There's lots of patchiness, lots of different colors, and that corresponds to darker areas where there's a lot of variation. So that's one way to do this. And just to be clear, as it's doing the calculation, it's moving 1 cell by 1 cell. So it's sort of a moving average. Let's switch back to the other type. So it would look at this cell here and look at all 9 of its neighbors, and then it would move over, the calculator moves over 1, and then it looks at all of its neighbors. So it's a moving grid. So we're going to look at a different way of doing this. We're going to look at the block statistics tool next. We're going to ask the same question, but using a different tool. In this tool, instead of moving 1 cell by 1 cell, we'll actually move we'll move to a completely new area each time. So let's actually go back to our previous extent. Actually, that's pretty good there. Gives us a good view of everything. Okay, so back to geoprocessing, to our search bar, block statistics. Oops, block statistics. So we're going to leave our parameters the same. So land cover for the input. And this time we're going to give it, the name we're going to give it is LC, land cover, variation, VAR, block. Block. And we'll do the same thing here. 10 by 10. We're going to go cell by cell, and we're going to go with variety. So there's our parameters, the same as the other one, just a different tool. Run the tool. Again, this is going to take a while. So here we go. Let's do the same thing. We're going to, as far as symbology goes, I'm going to give it the same color ramp. And I'm going to use this trick I've done before, where I'm going to import the symbology from our other layer. Symbology layer. It's going to be this. Okay, so I could have just picked the same ramp, but I kind of like to import it directly from a layer because then I know that it's exactly identical. So let's toggle this, toggle back and forth between the two different tools. So you can see that this the block statistics gives us a chunkier output, and that makes sense because we're moving over 10 cells at a time. Whereas, actually, let's zoom in so we can see that a little closer. Let's go to this high variation area. Toggle that off. So much higher granularity. This is just moving one cell at a time. So important difference between these two tools. Okay, so now we are going to look at another kind of neighborhood function to do something entirely different. So let's turn off the two feature classes we created. I want to zoom out, get a kind of a bigger look. So we can see this whole layer. Now, this is obviously land use. This is probably a layer that was generated from a satellite image and just coded into these land use types. And as we know, it's a raster. But let's suppose that we wanted to convert this into a vector file. So points, lines, and polygons. And we want to use these land classes. If we were to try to directly convert something like this into polygons, with all of these tiny areas, these little blips and blobs, what we would end up with is a real mess. So before we do something like that, before we try to turn this into a vector file, we're going to need to simplify this. So it's much smoother and much more homogeneous and generalized. So we're going to go back and we're going to use the same tool that we used before to just kind of clean this up and smooth it out. So go back to your geoprocessing selection pane. Let's see, I'm in favorites. I want to pull up focal statistics. So we're going to input land cover. So this layer right here. And we're going to name this Major 5. Major 5. So we're going to stick with rectangle, and then we're going to do a smaller area than we did before. We're going to do a 5 by 5. And the statistics type we're going to use is majority. So let's go into our information tool and see what that means. So it calculates the majority, the value that occurs most often in the neighborhood, in our 5 by 5 neighborhood. So it's essentially going to smooth out all of these grids, all these little areas that have a lot of variation. So run the tool. And this is my tool that ran. I put the recording on pause. So we're going to run this again. Essentially, it's like passing it through another filter. So we're going to do another round of smoothing on this. So now we're going to make our input raster, the one that we just ran, Major 5. And we're going to leave all the parameters the same. But we have to change the name. This X is here because we can't overwrite it. So we're going to call this Major 5 times 2. And run it again. Okay, and here we are with the next outcome. So we're going to symbolize this, and so right click on your major 5x2, go to symbology. And we're going to use that same trick that I just used before, where we're going to import symbology. Only this time we're going to import from a layer file. If we do import from layer, then we'll have the option to select from a layer that's in this project, but we're going to navigate to something that has been prepared for us. So I'm going into I downloaded data from this class, MGIS data, Black Hills, and we want to do land use numbers. So there we go. Let's move out so we can see the whole thing. That's probably good there. So there's still some roughness in here. But let's compare this to the original, which has the same symbology, only these are the numbers, recognize these numbers. It hasn't been converted into the names of the land use classes. So compare your results to the figure in the tutorial, figure 11.33. Make sure your original land cover and your land cover after 2 passes look similar to what we have in the book. Trying to pick an area. This is probably the area that's about similar to the text right here. So it should look something like this. My colors look a little different. This is blue in my textbook, but the rest of it looks pretty similar. Okay, so that brings us to 34. This is actually the end of one section, the neighborhood functions. But we're going to jump right ahead into the next one, converting rasters to features. Since we've been talking about doing that with this layer, let's just roll right into 35. So we're going to do raster to polygon. Go to your geoprocessing, back to your search. Raster to polygon. So for our parameters, we're going to, our input parameter is going to be major 5x2, so that's our 2-pass land use layer. So field, that's going to be how the new polygon is going to be assigned, how the values are going to be assigned. And in this case, remember that our values are our land use types, coded as numbers. Obviously, object ID would not be a good option. So we're going to name this land cover poly. And we're going to keep the box checked for simplified polygons. So as we know, this isn't super smooth. So by keeping this checked, it's going to help smooth this out more as the conversion is being done. So run the tool. Okay, so this is the output of that tool, and it looks like the beginnings of a polygon, but we need to do some work to this still. Let's take a look at the attribute table. So these numbers here should look familiar. These are our the number codes for our land use types, but the land use types did not come across. So we need to bring that in. So we're actually going to do a join. So I'm going to do it this way. I'm right-clicking on the land cover poly. I'm going to joins and relates. Add join. You could go through the geoprocessing pane, but I'm used to doing my joins this way. So our input join field is going to be that grid code with our land use number codes. So we're going to join this to our land cover table. If we open this up, move this out of the way, cover type is what we want to bring in, and the values here are the equivalent codes. So we're going to use our land cover as our join table, and then value is what's going to match this table. Open that up, the grid code. These are the same numbers. So let me close this, and if we validate the join, it actually found a 1-to-1 join and 925 matches. So we'll run our join, and here we go. Here's our cover type. So now we can symbolize, we can export this and symbolize it. So let's export first with the join. So right click on your land cover poly, go down to data, export features. So land cover poly, I've got my default database set to special chapter 11 geodatabase. You probably have yours on your raster analysis, which is perfectly fine. My output name is going to be land cover final. My final, and run the tool. So let's take a look. I'm going to open up the table, make sure this worked. So there's our grid code and the value that came from the land cover table, and here's our cover type. So we can symbolize now based on the cover types, which we will do. I'm going to remove the land cover poly, and let's symbolize on this one. So we'll do unique, since there's not really a numeric relationship, because it's just really categorical. And we're going to use the field cover type. Now I've got these funny nodes in here where there's no data. So it's not perfect, but it's a good example of how we can. And here we have our new categories. I don't know that this pastels is the best. So unfortunately, in our color ramps, we don't have a selection that matches the color ramp from the raster. Ooh, and that doesn't work very well at all. Oh, that's a little better. It could take a long time to fiddle with this and get it right, but you should have something that looks like this. But this is a good example of how we convert. Okay, so we're going to actually go back to our snail habitat, and let's say we wanted to convert our snail habitat into an actual vector layer after doing all that work to identify the absolute perfect snail habitat far away from roads. So go back to your home geodatabase, find your snail habitat layer, which we took the map out, so we'll need to get our feature class. So bring your snail habitat over into your map. And while we're at it, let's turn off our land cover, since we're done with that. Turn off all the land covers. We only want our snail habitat. Oh yes, and it brought in all these lovely colors. Just so this isn't like too awful to look at, we'll change our null value to 20% gray. So the problem with this is we've got two values here. We've got 1, which is our snail habitat, and also 0, which is everything else. And we don't want everything else. All we want to do is create a polygon layer of our snail habitat. So let's take a look at our table. So this value is something that would come across if we use the conversion tool. So what we want to do is we want to change this 0 to a null value, or no data. So we're going to do this using the reclassify tool, which we've used many times now. Let's see, I seem to have lost it, so I'm just going to type this in the search. So our input raster is our snail habitat, which is here. Reclass field is going to be value. And so we're going to change the output value in this new column for 0, which we want to get rid of, to no data. And then for 1, which is our snail habitat, we're just going to make that 1. If you look at figure 11.34 in your book, it shows this table and what it should look like. So that looks good. Oh, we need to change our name, the name of our output, to snail. Snail tab only, and run our tool. And as you can see, let me turn off that. The only thing that came across was our snail habitat, which is exactly what we wanted. So it's still a raster. We have to convert it now from a raster into a polygon. So we'll go back to our tool, which is raster to polygon. Input raster is snail hab only. Field is value, and then we're going to call this snail hab poly. And we'll keep all the defaults and run the tool. And there we go. Our snail habitat is now a polygon layer. And it's actually made each one of these polygons a different feature. Let's zoom to, yeah. So if we didn't want that, instead of having a big long table like that, we would just do this, check this box, create multi-part feature. So that means that it's one feature with multiple parts that are separate. And that's something you just take in consideration depending upon what you're doing. So that brings us to the end of this section. That was step 41. Check and make sure it should look something like figure 11.34a, your polygon layer. Whoops. And I'll clear my selection. And that's it for neighborhood statistics and converting rasters into polygons tool. And there we go. Our snail habitat is now a polygon layer. And it's actually made each one of these polygons a different feature. Let's zoom to, yeah. So if we didn't want that, instead of having a big long table like that, we would just do this, check this box, create multi-part feature. So that means that it's one feature with multiple parts that are separate. And that's something you just take in consideration depending upon what you're doing. So that brings us to the end of this section. That was step 41. Check and make sure it should look something like figure 11.34a, your polygon layer. Whoops. And I'll clear my selection. And that's it for neighborhood statistics and converting rasters into polygons. So here we are at the part where if you need to take a break or need to go back and rework any steps, do it now, and then we'll start with the next section. So here we are at the last section. We're going to do steps 42 through 51. Interpolation's really important when we don't have a complete picture of all of the data. There's a lot of tools that ArcGIS has for doing interpolation. We're just going to work with one. There's lots more though. And then zonal statistics. So we are going to start on step 42. I've got my map up from the last section, which I'm going to save and then close down. Let's see, I've got catalog open. We're going to open up one of the other maps that have been provided for us. So climate stations. I'm just going to close topo function since we are done with that. Okay, so the setup for this part of the tutorial, we have a map here. These are watersheds, which should look familiar to everybody. We worked with these in the last chapter, in chapter 10. This is the watersheds over the Black Hills area. And this is all vector. Watersheds are a polygon layer, and then we have these climate stations, which are discrete points. And let's look at the attribute data we've got. Cities. And here we have precipitation, all precipitation for the year 97, and then monthly totals. This is in centimeters. And if you toggle all the way to the very end, we have the sum of precipitation from all of these months. And this is what we're going to be working with. So this gives us the summary of all the rain that fell at each of these points. And what we want to do is to estimate or interpolate how much rain fell in between in these areas where we don't have any data. And we're going to do that by generating our own rasters. Before we do that, we were using a grid set to 30 meters, and this is a much larger area. If we stuck with our 30-meter grid where each cell is 30 by 30 meters, it would take forever to do the processing. And that's because, as you know, each cell has a value associated with it. And when we're multiplying rasters, the function has to be performed on each cell. So in order to shorten our processing time, and because this area is much larger, we don't need that fine a detail, we're going to go into the environments and we're going to change it to a much larger grid size. We're going to go from a 30 meter to a 200 meter grid size. That's going to dramatically cut down the amount of data we're going to have to process. And this is going to save probably a lot of frustration, because this is going to save everyone lots of time sitting watching tools spin and potentially locking up the software. So be prepared when you do run our tools this time. Probably still going to take a while for the tools to process. So let's go up to, we're going to go to analysis, inside the geoprocessing group to environment. And then for our processing extent, we need to set that to climate stations. And then for snap to raster, just clear that out. And for raster cell size, we're just going to enter the value 200. So it'll automatically use the unit associated with the feature class. And click OK. So the first thing we're going to do, we're going to create a raster using that sum field from the annual precipitation. So go to your geoprocessing, to your search, and what we want is the IDW. So we see that it interpolates a raster surface from points. So our input points, and note that it's looking for a point feature, climate station. The Z value field is going to be sum. So it can be the sum of all the precipitation. We're going to name our output raster and precip. Oops. And precip in centimeters. Output cell size 200, we've already set that in environments. Search radius, we'll leave that variable. So this should match also figure 11.35 in your book, and run the tool. So here is what the output was. It looks pretty good. Now, one thing of note, we're interested in this watershed. This black outline is our watershed. And there's lots of weather stations inside the watershed. But once you get outside and you're far away from other points, the formula really kind of falls apart because there's no data nearby. So we don't really know. I mean, maybe there's a ridge here, maybe there's some reason why there would be an extraordinary amount of precipitation or not. Maybe there's a little valley here that's dry. We just don't have any data over here. So what we want to do is not use any of this data on the outside of the watershed. We want to actually turn that into null data. And we're going to use this by creating a mask. So go back to your search pane in your geoprocessing and type in extract by mask. This is essentially same thing as doing a clip. We're cutting everything off on the outside and keeping what's on the inside. So we're going to set our input raster to nprecip, the raster we just made. Okay, and our feature mask is watersheds. And then we're going to name our output precip mask. Run the tool. So let's turn off this the annual precipitation. And what we want to do is come up with a better symbology. So let's open up the symbology pane for this. And we're going to use a stretch method, which we've defaulted to, but we want to change the color ramp from a brown to green color. So let's use my trick of showing names. It's just so much easier to find your colors. So if you're doing elevation, here's all these standard elevation ramps. So it makes life easier. Verdant tones, terratones, voxel, sequential. There's actually some pretty interesting names. It's kind of cooler to see the names. Okay, here we go. Here's brown to green. So let me, actually we're probably done with this one. Let me turn off the topographic. And if we click out here, it did indeed work. This is what we were hoping would happen. There's no data outside, but inside. So we actually can also mask in another way, which they didn't tell us about when we started this. But we'll go back and let's take advantage of that. So just so you know that this is possible, we're going to go back into environments. And we're going to set the raster analysis mask to our watersheds. So now every time we process a tool, it will automatically just cut off anything that's outside of these watersheds. So for the next part of this section, we're going to calculate the amount of precipitation in volume received by each of the watershed. And this is just after step 46. The formula is in your book. Essentially, we need to know the depth of water times the area. So we're going to do this using the raster calculator. So back to geoprocessing. I'm going to go to my favorites because I'm thinking it's going to be in my favorites. I do not see raster calculator in here, so I will enter it in the search. Raster calculator. So we're going to enter the expression precip mask times 0.4 zeros, 1, 2, 3, 4, 1 times 0.02 times 0.02. We're going to need the output precip volume kilometer. Let's do it this way. Precip volume km. Okay, so this is the result of that tool. And if you take a look at the scale here on the raster, this is extremely small numbers. And the reason why this is so small is because this is calculated based on each cell in the raster. So what we need to do is find a way to convert this into an entire watershed. So we're going to use a zonal statistics tool for that. So let's go to our geoprocessing search panel and type in zonal statistics. So what we're using this tool for is to calculate statistics based on a zone that we define. So let's just do this by demonstrating. Our input raster is going to be, so if we mouse over, this tells us that what this is looking for is the input raster. It's how we're going to define our zones, and that is going to be watersheds in our case. So we're going to select watersheds, and then there's a bunch of fields in watersheds since that's a polygon layer. So we want our zones to be our shed name. So this is going to be pretty cool. It'll give us our output correlated to the watershed names. Input value is going to be the raster. That's where we're deriving the numbers for our statistics. So that is going to be this one, the precipitation volume. And we'll name our output raster shed precip volume. And statistics, of course, we want to sum this up. We want to know the total volume for each of our watershed zones. And run the tool. And here's our output. We're going to give this a better color ramp than black and white. Yeah. So let's go into symbology. And we want, definitely in this case, I would say a blue, where's our blues? There we go. So this is the map that comes up, and you should have something that looks just like this. This matches the figure 11.37b in the textbook. Make sure that you used a white to blue color ramp, and it should look just the same. So before we move on to the last step, we're going to pause for a minute, and we're going to talk about a couple things relative to this map that's going to set us up for the last step. If you weren't familiar with this map, you hadn't built it like we have, it would just look like a vector map with a polygon and a point layer. But if you go a little closer, you can see the edges look a bit rough. So these cells don't match 100% the line boundary of the polygon of these watersheds. If I were to click on this to get data for the pop-up, it's giving me the attribute data from this watershed layer because it's on top. And that is what's great about vector data is you have a feature and you can associate endless amounts of attribute data. Now, if I turn this off and I click in the same area, this gives me the raster data. And as we know now, there's a single value associated with each cell. And you can see the cells or the pixels along the edge of the watershed. Each of these is 200 kilometers square. So let's close this. I'm going to turn back on watersheds and let's go back to our extent. So we've only associated a single value with all of these rasters inside each watershed. And the data we collected is the volume of annual rain received by each watershed in cubic kilometers. So we ran a couple tools to create this. So we're going to look at a different way that we can use zonal statistics to collect data. And in this case, we're going to create a standalone table where we use zonal statistics, but we're going to have multiple attributes in it. So instead of creating another raster, we're creating a standalone table. And this time we're going to do this one, zonal statistics as a table. And we're going to set this up the same as we did for the last tool, at least for the beginning. Shed name. So we're going to recalculate essentially. Oops, that's the wrong one. Kilometer is the one we want. Precip volume kilometer. And our output table, shed volume table. And yeah, for statistics types, so we're going to get all of these. Now this can be a little bit of like going to the buffet and with eyes that are too big. It will give you a lot of data. So if you knew what you're looking for, you could go through and you could just pick a few of these or one of them. But let's go ahead and run this. And so here's our table that we just generated. So let's open it up and take a look. So here are our zones, our watersheds, and all of the different statistics that we asked for. So what's useful about this is now we can go back to our watershed polygon layer. Here's our shed names, and we could join this table, the standalone table, and now we've got the volume per watershed summarized in all kinds of different ways. Min, max, range, yeah, and on. So another useful way that we can use zonal statistics. And that brings us to the end of this section and this tutorial. So congratulations for making it this far. And here we are at the last time for our pause and explore. Go back and rework the steps, review what we've done. This will be useful information for the homework, and good luck with the homework.